Hello AP Chemistry and welcome to the back part of Chapter 15, which is actually selected sections from Chapter 17. Obviously we will finish the rest of 17 when we do 16, right? We've just picked out the parts that mesh well with 15 to go here, and the rest of it will get lumped in with acids and bases, right? But everything we talk about here in this part of Chapter 17 is stuff we're familiar with, right? Like the concept of solubility. That's something we've been talking about all year, right? Where when we say that something is soluble, we mean that it does dissolve in water, right? If it's ionic, if it dissolves, it will also dissociate into ions, right? And solubility is the extent to which it will dissolve. Yes, the extent to which it will dissolve, right? And this goes back even to last year when we talked about our solubility rules, right? And remember that some of them had the little asterisk on it, right? Which means like they're slightly soluble, right? What does that really mean, right? And we've talked about this year that when we say that something is insoluble, that doesn't mean that 0% of it dissolves, right? It just means that such a small amount dissolves that we consider it essentially negligible. But once we start talking about equilibrium, right, reactions going forward and backwards, right, then these little things can start to matter, right? And you'll note that Chapter 17 is tied to acids and bases, right, and the concept of pH, because a lot of this does also have to do with pHs of solutions, right, in that some of these dissolved ions have effects on pH, right? Which we'll finish that picture out in the next unit. All right, so for starters, again, solubility is the extent to which something dissolves in KSP, solubility product constant, right? So we've talked about Kc, where that's the equilibrium constant with respect to concentration. Kp, which is the equilibrium constant with respect to pressure, right? If you think back to last year, right, you'll remember we talked about Kb, which is like the autoionization constant of water, right? Which, oh my gosh, that's an equilibrium constant, right? And now we're going to talk about Ksp, right, which is the solubility product constant, which is always, right, for the dissolving of an ionic compound in water, right? So let's write some just to get us started, right? So for example, here we have AgCl, right? So what that means is AgCl, solid, dissociates to form Ag and Cl minus, right? And this is the equation that goes with that KSP, right? So then the KSP for this is equal to Ag plus and Cl minus, right? And that's it because pure solids and liquids are excluded. Yes? All right. And let's go ahead and write this in. This is equal to 1.8 times 10 to the negative 10, right? Also, though, we could have this one, right? So lead 2 fluoride, solid, gives us some lead and also 2 fluoride, right? And so then the KSP is equal to Pb and F minus, right, so the second, right? Because so note that we don't bring that 2 in there. That 2 is what goes and becomes the exponent. All right, and this is equal to 3.6 times 10 to the negative 8th, right? So as we look at these, right, it is clear, right, that this, right, versus this, which one is the smaller value, right? So this is the smaller KSP, right? Which you might think, oh, well, that means it's less soluble, right? But remember that KSP is not the same as solubility, right? Solubility is a concentration, right? Usually in molarity, but it can be grams per mil or grams per 100 mil, right? But it's about the extent to which it dissolves and needs to reflect a concentration, right? So all we know is the KSP, but from that we can come up with the solubility, right? So let's talk about how to do that, right? Solubilities are these. These are the solubilities, right, for those respective ions, which we can then, using stoichiometry, tie back to the actual compound, right? So that requires us to be able to solve for them. So if we think about this one, for example, KSP is equal to Ag times Cl minus is equal to that, right? Which is actually just x squared is equal to 1.8 e negative 10, right? Which means that x is approximately equal to like 10 to the negative 5-ish, right? And that's approximately the concentration of my silver ion and my chloride ion, which is in a 1-to-1 mole ratio with AgCl, which means that the approximate solubility of silver chloride is 10 to the negative 5th molar. Yes? And if we look down here, right, this is X times 2x squared, yes? As in the concentration of lead is 2, the concentration of F is 2x, and then we square it, which means that this is actually, right, 4x cubed is equal to 3.6 times 10 to the negative 8th, right? Which then, when we do that, so that's the cubed root of 8, which is like 2, right? Which means that x is approximately equal to 10 to the negative 2. And so that's approximately the solubility of lead, which is then approximately the solubility of lead fluoride, right? So then when we look at these, right, yes, in this case, right, so this is the approximate solubility, and these are the respective KSPs, yes? I guess I could have picked different numbers and come up with a different answer, right? But does that make sense, right? Solubility is not the same as KSP, right? Tiny KSPs reflect low solubility, right? But everything that we write a KSP for would have a relatively small KSP, right? If we want to come up with the actual numerical value for solubility, right, we would need to solve for this. And all those X's are just coming from Rice tables, right? We could write out a Rice table if we needed to. And if you're not clear on where I got those X's, come see me and we can work one out together. Note that this is all in contrast to, say, something like NaCl, for example, right, which is decidedly soluble, right? Because you'll note that AgCl, insoluble based on our solubility rules. Lead halides are insoluble, right? But NaCl, right, if we think about that, we would just say this. And if I asked you, oh, how much of the sodium chloride is left, you would say 0 because it's decidedly soluble. All of it dissolves and dissociates, right? And so it would have a KSP that is ginormous, right? Huge, astronomical, right? But we can have a situation, right, where it does become an equilibrium process, right? As long as we have both of these present, right? So as long as we had a saturated solution, we could still have an equilibrium scenario, right? Whereas for these insoluble salts, a saturated solution is easier, right? Because pretty much any obvious to our eyes amount is going to sit at the bottom, right? And some of it will dissolve and some of it will precipitate, right? For sodium chloride, though, right, we have to go beyond the solubility limit, which is relatively high because it's a solid salt, or it's a soluble salt, right? Does that make sense? Okay. Make sure you understand, again, how we come up with these X's here, because it is assumed that you could work that out on your own as needed. Low practice problems. So, a saturated solution of magnesium hydroxide in contact with that, so the whole point of saying that we have aqueous this and solid that is to tell you that this system is in equilibrium, right? If it is in equilibrium, then we can do what we just talked about using KSP and our solubilities. The pH of the solution is this, assuming that it dissociates completely. So what that means is the part that dissolves dissociates completely, right? Meaning that all of the hydroxide in the solution comes from the magnesium hydroxide, right? And there are no other simultaneous equilibria happening, right? Calculate KSP. So first, let's start with our equations, right? So magnesium hydroxide, right, in equilibrium with its respective ions, like that, right? And then it says that we have a pH of 10 to the pH is equal to 10.17. What's the significance of that? Right, the pH tells us about the hydroxide, right? Well, it tells us about hydronium, which can then tell us about hydroxide, right? So obviously we talked last year, right? There are multiple routes to get to our hydroxide ion concentration, right? So why don't we start by doing, say, 14 minus 10.17, which is going to get us our POH. And what does that give us? Right, 3.83, right? And 10 to the negative 3.83 is going to give us our hydroxide ion concentration. So let's go ahead and do that. And that's the concentration of hydroxide ion, right? So this is the concentration of this, right? And then we have to use our understanding of stoichiometry, right? Because if, so let's move this out a smidge, right? So if this is the concentration of that, right? then for every 2 moles of hydroxide, there is 1 mole of magnesium, yes? As in that's the relationship between them because they all come from here, right? Now that's the purpose of this statement here, that there are no other simultaneous equilibria happening, right? As in there is no other source of magnesium, there's no other source of hydroxide, nothing else is at play. All magnesium and hydroxide ions come from magnesium hydroxide, which means that we understand the ratio has to be 2 to 1. Yes, does that make sense? So then we just plug this into our KSP equation, right? So then we're going to have 7.4 E negative 5 times my hydroxide, which is 1.48 times 10 to the negative 4th raised to the 2nd power, right? And we would just solve for that, and that would give us our KSP for magnesium hydroxide at this temperature. All right, next up, in a similar but not exactly the same problem, it says the KSP for lanthanum 3 fluoride is this. What is the solubility, right? So again, solubility, right, is what goes into these parts, right? What goes into our KSP expression, and I know the KSP, right? So then I just need to come up with an equation. So LaF3 dissociates into lanthanum and 3 fluoride ions, yes, right? And so that means KSP, which is 2 times 10 to the negative 19th, is equal to X times 3X cubed. Yes, does that make sense? And then we would solve for X, and X is our solubility. Yes? All right, because again, solubility is what goes into the expression, right? KSP is a number that is a constant that reflects, in general, how soluble the compound is, right? Okay, thank you for listening. Be good. Stay tuned for the last chapter 17/15 lecture. All right, be good, and I'll see you soon. Bye.